Hello and welcome to today's video. Today we will be talking about Gaussian elimination as a means of solving a system of linear equations using tableau form. The idea here is that some manipulations are possible that do not change the set of solutions of a system of linear equations, but that do change its tableau form. And what we want to do is we want to combine these solutions in a way that leads us to echelon form. And then using this echelon form and backward substitution, we can solve the remaining system of linear equations. So today's section is called Gaussian elimination. As I said, the idea is some manipulations to the equations are possible, don't change the solution space. So for a system of linear equations, some manipulations to the equations possible that do not change the solution space of the system of linear equations. In particular, what we want to do is the following: three manipulations. The first is we can exchange any two equations. The order of the equations in a system of linear equations does not matter at all. So we can exchange the order of any two equations. And for tableau form, what that means is we can rearrange the rows of a tableau. The second manipulation that can be carried out is we can multiply an equation by any constant as long as it's not zero. Of course, if we multiply by 0, the whole equation becomes 0 equals 0. So the information given through that equation is effectively lost. But any other constant is fine. It scales the equation up or down, but it does not change the solution set. So we can multiply an equation by a constant number other than 0. And finally, we can also add two equations. To be more precise, what we can do is we can replace an equation by the sum of itself and some other equation. And in combination with that second idea, multiplication of an equation by a constant, what we can effectively do is replace an equation by the sum of a multiple of itself and a multiple of some other equation. Okay, so these three ideas can be translated into tableau form. And through successive application of these three steps, we can transform our tableau into echelon form. And that is basically the idea of Gaussian elimination. So these operations can be translated into the tableau representation of a system of linear equations. And then through successive application of these operations, we can obtain tableau form. So that can be used to transform the tableau into echelon form without changing the set of solutions. And that is what we will be doing in the so-called Gaussian elimination procedure. Let's sum this idea up in a theorem before we see it in practice. So for a system of linear equations in tableau form, there's a number of row operations that leave the solution space unchanged. We'll just list that in tableau form now. For a system of linear equations in tableau form, the following row operations and these are called elementary operations. Those operations leave the solution space unchanged. And those operations are basically the translation of what we've just seen into tableau form. So the first operation here is we can exchange any two rows. And of course, by successive exchanges, we can basically alter the order of the rows in any way we want. The second, we can multiply a row with a non-zero number. And the third, we can add one row to some other row, or even a multiple of one row that combines that operation 2 into the summing process. So we can add a multiple of a row to some other row. And the interesting fact about this is now every system of linear equations can be transformed into echelon form without changing the set of solutions by just applying a finite number of these elementary row operations. So that's what the theorem says. Further, every system of linear equations can be transformed into echelon form without changing the set of solutions. And this can be done by applying a finite number of successive elementary row operations. So the question that remains is, of course, how do I apply these row operations in a systematic way? And we'll sum up that system in the so-called Gaussian elimination procedure. So how do we proceed here? We start by translating our system of linear equations into tableau form, of course. So start with a system of linear equations in tableau form. Next, we locate the leftmost pivot elements, or one of the leftmost pivot elements. There are usually several candidates. Basically, what we want is any non-zero element is fine, and we want the leftmost non-zero element in our tableau. Then we designate this our pivot element and move the row to the top of the tableau by doing row exchanges. So we locate one of leftmost pivot elements. That is, we can choose any non-zero element here. And then move its row to the top of the tableau row exchanges. Second thing we do, and then we use this pivot element and the corresponding row to produce zeros in the tableau below that pivot element. That is idea number 3. Basically, sketch of what we're doing is we start with the tableau. Any entries in there? We select one of the leftmost elements that are not zero. Let's say select this element here. The corresponding row. And then we move that to the very top. So this is our first step. Third step will now be to use this element here, start pivot element, to produce zeros below that element. And we can do this by adding suitable multiples of that first row to the rows below. So that is step number 3. Use addition of suitable multiples of the pivot element selected in step 2 to turn every entry below the pivot to 0. And that is obviously the first step towards echelon form. First staircase step here. And what we're going to do next is we're going to leave the first row and the first column unchanged from now on. We concentrate on this part here and repeat the procedure on that green part. Basically, we just don't touch the first row anymore. The first column, we can touch that one. That contains zeros anyway, everywhere in that green part. So from here on, so whatever we do with the remaining green rows does not change the first column anymore. So remark that. The first row will stay fixed from now on. Part 4 is then repeat that procedure for the remaining rows. Okay, but do not change the first row anymore. And if we do this successively, what we will get is a tableau in echelon form. And once we have that, of course, it's easy to determine the solution space. We just use back substitution for this one. Let's just sum up this idea as well. So the next step is then to determine the solution space. From echelon form. And we do this in the following way. First thing we look at is the 0 rows at the end of the tableau. If the tableau contains 0 rows with a non-zero right-hand side, then there cannot be a solution. We can terminate right away. So if the tableau in echelon form contains a 0 row with non-zero right-hand side. Then the solution space is empty. If that is not the case, we perform back substitution to compute a solution. Or rather, the complete set of solutions. When we do this in the following way, we know that every column of the tableau corresponds to a variable of our system of linear equations. Columns that do not contain a pivot element correspond to free variables or free parameters. Those may take on any value, and each choice for that value gives us a different solution. For the columns with pivot elements, we can just use the pivot row, the row that contains that pivot element, to solve for the corresponding variable. So the idea here is the following. Every column corresponds to a variable. Columns with no pivot element correspond to the so-called free variables. Or sometimes we will also say free parameters. And what does it mean? Well, that means these variables can take any value, and each choice of a value for those yields a solution for the system. Those may take any value, and each choice of a value yields a feasible solution for the SLE. And then we have the columns with pivots. So for columns with pivots, we can solve for the corresponding variable. Using the row that contains the pivot. And of course, that solution will depend on the values of the free variables. So for each setting of the free variables, these pivot variables, these non-free variables or bound variables, will assume a different value. So that solution depends on the values of the free variables. So for each value of the free variables, these so-called bound variables will assume a corresponding value. In the solution. Okay, so you can choose your values for the free variables. You cannot choose your values for the bound variables once you did that. Finally, one last remark. The number of free variables of a system of linear equations, how large is that number? Well, that depends on the number of pivots that we have. We have n variables, and each pivot corresponds to a bound variable. So n minus the number of pivots is the number of free variables. So the number of free variables for a system of linear equations with n variables in total is equal to n minus the number of pivot elements. So what I mean by this symbol here is the number of. Okay, so that completes the Gaussian elimination procedure and the solution procedure for a system of linear equations. In one of the next videos, we'll see this procedure in action in a couple of examples. I'll see you then.